There's a lot of links today. I think it's 8. So, I don't need that one.
Right click it and say open a new tab if you don't want to have to copy and paste over
So right click, just
like
right
on the
click.
link itself.
Oh, okay.
On your web page.
Oh, here?
Yeah, like if you right click on any of the blue links and say you can say open in a new tab.
Oh, all right. Well, I already got all the tabs open. The next time I'll do that. I mean, they're already open. All right, I'll do it.
Do you still have to copy and paste the URL?
No, I
Aren't they
did.
just
I already
tabs
did.
right now?
I already know. I already
Oh,
did
you
that.
already did it.
Yeah.
Sorry.
That's all right, though. I'll do it your way.
I should have said something sooner. My bad.
Open like a new tab. No, it's frustrating when you see someone doing something. It's like,
I didn't realize. I'm sorry.
I know the feeling. I mean, there's also the pig-headedness of not doing it. You know, it's like, which I'm trying to avoid. Yeah, that's much faster. I guess we can just dump these guys. I'll keep one of them. Or I'll open this guy. I'll keep one there. All right, so this is the thing. Let's see. How about how to get rid of this thing?
On the right, on the left thing, there's like a three, yeah.
Oh, nice, thanks. That's pretty helpful. All right, so this is Hilmar is a guy that does X-rays for the Materials Directorate at the Air Force Base in Dayton. So there's 2 people from the Air Force, Hilmar and Eric Trigg, I think. I don't know Eric Trigg, but he's the first author. There's 2 people from this NSLS 2. So let me find it. You can just do that and we'll find it. Yeah, but where's the, so it's a synchrotron, right? So this is NSLS 1. So when I was in grad school, this was a pretty big deal. So you can see there's going to be, this has 2 rings to it. One was for X-rays, one's for UV. So the UV rings for like X-ray lithography for photolithographic stuff. And they were both fed by the same, there's an accelerator here somewhere. So there's a particle accelerator that shoots a beam of, here it's electrons, and they go around the ring. And then as a charged particle changes direction, it gives off X-rays. If you get a high ring current going, you get really high flux of X-rays out of that. And they're monochromatic and they're collimated. So it's kind of like an X-ray laser almost, but you need to have this building to do it. So you can see these are cars, that's the building. And then this is the new one, which is significantly larger. Right, there's still nothing compared to like Kern, like the accelerator in Switzerland, France. I guess it's Switzerland and France. It goes across under the border. It's buried, you know. So they wanted to build a Kern at Brookhaven. This is online. This is where they wanted to build it. They got it half built. Or they kind of dug the dirt, and they found out that the magnets were like there was a flaw in the magnet design, so they dumped the whole thing. Right. So Brookhaven National Lab is on Long Island near New York City, kind of. New York City's there. So it's then Stony Brook University is kind of near here somewhere. Port Jefferson, Stony Brook. So SUNY New York is like here. Right. So then these are like quaint villages, and then this is the Hamptons from Gatsby, you know. That's Hamptons is where all the rich New York people go. So you can see even pretty far out, you can see that collider thing. Anyway, that's where this work was done. So let's see, why did I lose the paper now? I didn't, it's here. All right, so what they're looking at is epoxy. And I didn't. So there's a wiki page for epoxy. So it's basically this, let's see, oh, those guys are here. So it's this, that ring is called an epoxy ring, you know, so it's got 2 carbons and an oxygen. So when rings get that small, they aren't stable. So you can kind of pop that open easily, you know, so you can pop it open with, in this paper they're using, so bisphenol A is this thing with 2 aromatics and this kind of T thing in the middle. It's got two hydroxyls at the end. That's like polycarbonate. Bisphenol A is makes a polyester with polycarbonate. So polyester has got these ether linkages. And this epoxy is also going to have like ether linkages all over the place. And if you cure it with an amine, like a diamine, then you're going to get a network forming out of this thing here. So that's kind of the basis for fiberglass, you know, for sailboats and things. And then it's also for airplanes, because it's a low weight, strong material when you put glass fibers into it. You can put carbon fibers, glass fibers, you can put nanotubes. Right, so this is kind of a conventional study. So the idea is you're going to react that with these amines, and they're just going to pop the ring open, and then you get something like a polyamide, or you're going to get a, what do you get out of that? It's not a polyamide because it's not a double bond, but you're going to get a linkage between these anyway, and it'll form a network. So it's gonna make a network if you use a difunctional. If you use a monofunctional, you get a linear polymer out of this. This guy will have like 2 linkages to it. So each of these, so this will be like a tetrafunctional. So if you have a network, you call this F, the functionality, small f. And then, so small f becomes like the number you use for the network. So that thing's going to give a tetrafunctional network. So, oops, that's red. F is 4 for this thing. Okay, so you can go to, so it's going to start reacting. So you're going to have your bisphenol A with that epoxide ring, and then the amines are going to attack. This will open up into 2 linkages. And whatever, and there's another N over here. So those things will have 4 and they'll hook to an oxygen. It's going to eventually react until it's like a completely reacted network. Right, and along that process, it'll turn to glass. So this is a really low viscosity liquid to begin with, like basically the viscosity of water. So you can just soak fiberglass with it, just pour it on. It could be different viscosities. You can put different, you can have a pre-polymer here, so it could be more viscous if you want it to be. Depends how much you want it to stick to the fiberglass. And then, or it could just be like water. And then if it's like water, it'll make it glass sooner because it will have less change between. So it'll have a lot more of these cross-link junctions. So it'll vitrify sooner. Right? So depending on, and if you want it to be like a looser, like a tougher network, it's going to be more flexible. Then you put in a single amine in there, and then that's just going to make a linear polymer through this thing, right? So we'll just make a linear chain if you have a single amine. So that's kind of the idea. So all right. So the basic concept is that people have about this is it's a mess. It's kind of like throwing a hand grenade into a room with gasoline around, and things just going to blow up. And you'd expect you'll get blotches with a lot of cross-linking, and then some with a lot less, because it's not necessarily thought of as a controlled reaction, right? So usually people, and then every problem you have with it, they talk about the heterogeneity because of these like regions of high reaction and low reaction, right? So that's, I think, the common thinking. That's how I think about it. But this paper pretty much shows. So the measurements you can do NMR, and you can measure how many of these, like the number of those epoxide rings that still exist, and then the number of the amines that are still there, and the number of the single, and then the number that have totally reacted to that. So you get numbers for all these. So you can get locally on an atomic scale, you can get an exact measure of how this reaction is going. Right. So you can say, for instance, what's the probability that one of these things will react? And then if you want to, so you can get a probability for all these reactions to happen, and then you can figure out how this network grows. Okay, but you have a sample that's going to be like a centimeter, right? And this is basically like 0.1 nanometer size scale. That's NMR. If you're looking at just this really local thing, and then you think that this kind of thing happens, and you don't have any idea like what the distance between those things are, that you don't even have any evidence that they really exist, right? So this is the kind of the issue here, like what's really happening. So you can also do DSC. So you can measure the glass transition. So you have like CP, this temperature, there's going to be this glass transition that happens. And then you're running the reaction at some temperature T. So so as the reaction goes on, then this thing shifts over. The glass transition shifts with the reaction. So once that crosses the room temperature, wherever you're reacting at, this is actually reacting at 110 C. Then it'll turn to a glass, and then you have this vitrification. Then supposedly all the kinetics stop, like everything really slows down. Right, so when it's over here, all these low molecular weight molecules are just flying around, right? So that they're following diffusive motion. So you expect that x squared would go with the time. And then once it crosses that and it vitrifies, then that's postulated that you have like stress relaxation is the model. And then you have like somehow it was stressed while it was reacting, and then it locked in. Then the motion of things is going to be ballistic. It goes to power 1 here. All right, so that's a hypothesis that isn't really proven. I mean, but somehow, if you say you have everything's on a rubber band, and then when it locks it in, and then when it moves, then it's only going to go the direction of the rubber band pulls it. So the idea is that's going to be a one-dimensional motion, like a bullet. So anyway, so that transition from two-dimensional, or from this kind of diffusive motion, the Brownian motion, to this kind of ballistic motion is observed. It was previously observed, and it's observed in this work too. And then the model for that is a stress relaxation thing. So there's a lot, even though this is 1930, then maybe 35, this was invented. Okay, and then now it's like 2000, almost 30, so like 100 years almost, right? Still, there's interest in this, and this, right? The chemistry of it has been manipulated over the years, and it's still being manipulated. So what, like bisphenol A or whatever you want to put in the middle between the epoxide rings, and then whatever amine curing agent or whatever you want to use. So people are tweaking with it to try to get better performance for things like airplanes. So the Air Force is really interested in this. Also, there's a lot of work, not in this paper, but if you have the glass fibers, or you have a carbon fiber, or it could be nanotubes, then that isn't necessarily, so you have kind of polarity here, and glass fibers have hydroxyls, but carbon fibers don't, right? So you have to figure out how, so carbon fibers are superior to glass fibers. They're stronger, much stronger, right? So but the interface between the carbon fiber and the epoxy is not great, right? Because this is polar and this is polar and this is non-polar. So you have to have some kind of coupling agent between the fibers and the matrix. So that kind of thing. So like Michelman makes Michelman's a company in Cincinnati. They make the coating for the fibers for carbon fiber. One of the things they do. They do a lot of things. One of them is making coatings, which is called sizing for carbon fibers to make them match up with the epoxy matrix. So there's a lot of money in all this stuff. In other words, the way that if you want to make an airplane or something, then you make it out of fiberglass or some kind of composite like this. And there's a huge amount of money in that, in the military, but also domestic. And also if you want to make a surfboard, you got to use the same technology. So it's used for good and evil, you know, so it's kind of like it's there. So this scientist are just kind of pawns in a bigger game here. So anyway, so you can think of this as like a death science, or you can think of it as surfboards, however you want to think about it, you know. Anyway, it's there. So there's that's the epoxy resin. All right, so then he's going to do, the reason I picked this paper out is because it's used in XPCS, which is kind of like dynamic light scattering with X-rays. So you go down and he's got the dynamic light scattering equation here. So he's got this G2, the correlation function that I talked about last time. And this is G2. So G1 would just be this exponential term. So the exponential decay in time, tau's the time. Right, so you're going to measure as a function of time. And you're going to watch an exponential decay. You're going to do this gamma. And the gamma is going to be two times the diffusion coefficient. Right, and so basically gamma is going to give you the diffusion coefficient. You get the hydrodynamic radius from that. So you stick the epoxy in the beam and you get no signal, like there's nothing comes out. So that's a problem. So to get around that, and you're trying to see how the dynamics change through the cure of the epoxy. So then they go to something that's just like DWS, diffusive wave spectroscopy. So they're going to dump a load of nanoparticles in. And then the nanoparticles have contrast, so you can watch those move around. And they're at the same time, they're probing the viscosity of the matrix, or the viscoelasticity of the matrix. So the more viscoelastic the particles move with different frequencies. And from that, you can get, so it's the same thing as the diffusive wave spectroscopy. You're using a probe, a particle, and this is called microrheology. So you have the viscometer, where you move the top thing and oscillate it, go through frequency, all right? And then you have this method, which is going to use, so he describes it pretty well in here somewhere. I don't see it right now, but this is actually a pretty good paper, not because it's got profound results, but because it's really good work. I mean, they did a really clean study. They really looked at the literature, and everything is clean. There's nothing wrong with this paper, except there's a couple things wrong, but I can talk about it later. But basically, so this is basically the viscosity would be like the diffusion coefficient. So it's going to follow Einstein-Stokes law. So you have kT over 6 pi r radius of the particle times the viscosity is Stokes' law for the diffusion coefficient, right? So this is almost the same thing. It's got like kT on top. It's got the pi, not the 6, and a is a radius. So that's just like Stokes' law. And where you have the viscosity, you have this thing. This is a gamma function. It's like an exponential. It's kind of like an exponential so exponential would be like 1. It has to be an integer, like 2, 3, 4, 5. Like 3 times 2 times 1. But if you have something like 0.8, you can't do an exponential, but you can do a gamma function. So gamma function is kind of like an exponential. It's an integral function, but it's basically like an exponential for a number that isn't an integer. I mean, I don't know if that helps any, because it doesn't help with describing what's going on here, but that's what a gamma function is. It's like when you have if you wanted to do what is it called? Factorial, where you have then if you want to do that, then it's going to be this thing if it's non-integer. So anyway, so this thing's there. Alpha is some kind of thing. It has something to do with mean square displacement of these probe particles. And then this mean square displacement you get from G2. So G2, you can measure from that decay function. She shows one of them in here, I think. He shows all of it in the supplementals to this thing. Let me just go to the supporting here. So he keeps referring to the supporting. For instance, this is a scattering pattern from the particles, right? So that's important to know. And he's measuring at 0.011. So he's measuring like right here. And then, so this is Guinier's law. The knee thing is a log-log plot. And this is power 4. So they are like spheres kind of, except they're not monodispersed spheres. You can see there's some oscillations out here, but they aren't, it's polydispersed spheres. So why he chose polydispersed spheres is unknown. Like you can buy monodispersed spheres. These things have a standard deviation of like 1/3 of the number, right? So it's a pretty big distribution of size of spheres. But anyway, that's what he did. Maybe that's all they could get, I don't know. But I think that they also, the other thing is that they're using polystyrene spheres. They could have used silica spheres, which would have had a lot higher contrast factor in this thing. But anyway, so nonetheless, like that's the scattering pattern that they're getting. They're going to pick one of the Q's here and look at the time dependence of that. And then they're going to correlate that. So they're going to get that noise pattern. I don't think he shows the noise pattern. So they'll pick one of those, and they're going to get the intensity at that Q value, which is 0.011 inverse angstrom, and that it's going to have an average intensity that's going to fluctuate around because the particles are like moving in and out of the beam. Same thing as dynamic light scattering. So if you're looking at just that one particle, then you're going to take the time correlation function. So T, your probe T, and then delta T. So the delta T is calls tau. That's the difference. Then he's going to plot the intensity times the intensity of the two T's divided by the average of that over all T's. And that gives them this G2 number, which equals 1 plus G1. So basically that this G1 is going to go from 1, when time is 0, it's the same value, and it's going to decay down to 0. And that thing, that decay you fit with this exponential minus gamma t, your gamma tau, this is tau here. So then you get that thing, and that kind of gives you the dynamics of the thing. Right? So the problem here is that, so you're measuring this as a function of time, right? And you're looking at the cure of the system as a function of time. So as you go down this time road, this material is changing, like it's curing, and then curing is what you're trying to study. So that's called a two-time problem or something. Two-time. There was just 2 times. This is decay time with the motion of the particles. There's also the thing that's becoming more glassy as it reacts. So it's kind of like an unsolvable problem in a sense. But there is, so people are interested in this for some reason. So surprisingly, the papers on this two-time correlation problem have citations, like hundreds of citations. So I guess people are looking at this time. So this is his two-time correlation functions, and it talks about it. So nobody wants to do this because this would become like insanely complicated, right? Two-time correlation function. So the system's curing, and you want to know the dynamics of it at the same time. So what he says in this paper is because it doesn't change over so the time of the reaction, you can change with the temperature. So he runs it at 110 C, which takes 2 hours for it to run, and his measurement's going to be like 3 minutes. Okay, and he does some measurements. He finds out that the pattern, the decay pattern doesn't change. Oh, here he's got one of the decay patterns here plotted in a small thing. So it's just this decay thing. He fit in the red is the fit to that kind of exponential decay thing, this thing. So anyway, it doesn't change over the time that he's measuring it. So he says that he can use a one-time correlation function, meaning he can ignore the fact that the system's changing while he's measuring it. Right. So that makes things a lot simpler. Then he's got a couple twists here. So the exponential for dynamic light scattering is just an exponential. And if you have a problem, you say, well, there's many of these exponentials. Right, which there probably should be many of these exponentials if he's got a polydispersed spheres that he's looking at, because each size would have a different decay. But instead of doing that, he uses this thing called a stretched exponential. So you take the argument of the exponential and you raise it to a power. So it's called a stretched exponential. He calls it a compression exponent. In math, that's called a stretched exponential. So anyway, and usually this power here is used to tell what's called the fragility. If it's a glass transition you're looking at, you're modeling the dynamics with this kind of exponential decay, then that thing's called the fragility, that power, and then that's how you measure, that's how you can tell if you have a fragile glass or a non-fragile glass. So believe it or not, glass transition is like a huge area of research. Like there's a ton of people studying it for no really known reason, I think, because it's like, it's interesting, but it's a problem that will never be solved, I think. Anyway, so this fragility issue, there's conferences on fragility that people go to Europe and they sit around, drink wine and talk about fragility. They're talking about glasses, not about something else, but anyway, or the glass transition. So that's a big topic of its own, but he just says, I think he says this thing's like close to one and he kind of ignores it, which is a good thing to do with it. And then he gets this gamma. Yeah.
Isn't there, in some rheology circles at least, isn't there some thought process that if you could probe accurately enough the glass transition characteristics that you could extrapolate the entire master curve for the material below TG?
I haven't heard about that. I mean, the entire master curve means from like 0 time to infinity time.
Well,
And then
the master curve within the pertinent region of use for the material. Let me say it that way. Let me say it differently.
I don't know that much about it,
Okay.
I guess is the bottom line, but basically people are trying to get the full relaxation spectrum.
Right.
And then from that, you can tell all the properties of things at one temperature, So I don't know. The glass thing, it's a whole field to itself. So probably yes. I mean, I don't know. Anyway, I haven't really dealt with the glass transition stuff that deeply, So that's why I'm making fun of it, but maybe if I did it, I'd take it a lot more seriously. But basically, I haven't really seen that the fragility of a glass has ever been used to like save anyone's life, So I don't know. I don't see the relevance that much, but maybe there is relevance. I mean,
Well, in asphalt, I know, because it exhibits characteristic time temperature superposition behavior.
Uh-huh.
So you can use glass transition to extrapolate back into like a frequency space.
there's just a good talk on asphalt. A guy from Dow. Did you work at Dow or something or?
Marathon Petroleum.
Oh, okay. Anyway, Dow at the ACS meeting, which was partly online, a guy from Dow gave a long talk about putting polymers into asphalt and how the failure mechanisms of asphalt. And it was kind of interesting.
That's what I did for 4 years.
Oh, really? Okay. Like you can get ruts, or you can get like cracking, or you can get this cold, hot failure thing, and how when you add the polymer, it changes that. So it's kind of interesting. I mean, they're thinking about to use like waste plastic and mix it in somehow. And then Dow's good at that because they've developed all the copolymers to make it mix better. So maybe I could, yeah, I'm not sure there's that much physics in that talk though. It's kind of like really just, it was interesting though, I think. But so anyway, this is the thing, this thing's gonna go, it should, so this is time kind of, and this is size, so P should be 2. If it's diffusive. In other words, size squared goes with time. So P should be 2 by all rights for everything, right? Unless you have this, unless you lock it in, and then this P number would be 1 if it's ballistic. Then size goes with distance because it's a bullet flying through space with a fixed velocity. And he's saying He says somewhere in here that that would be like if the thing was stressed when it was locked in and then it's pulling back in. So it's just going in one direction. So it's not moving randomly. It's going just like directly. So he says that P is 1, very short cure. And he gives like, they give nice references for everything. So if you, and I looked up some of the references, but it's a pretty good paper, you know, like they're doing pretty good. So anyway, there is a transition in that thing. It goes from 2, so this is plots of 2 to 1, basically. Right, but and there's some difference, but you know it's good enough given that it's epoxy. You know, so that's his cure. That's where the thing is formed the network. That's where it's locked in, right? Where that happens. So believe it or not, he can tell when the thing locks in with this really kind of obscure measurement he's doing, right? So, and he shows that that works well here. So this is that measurement, his transition thing. That's where he says it's cured, right? And then he's got this dot, the square triangle, whatever, upside down triangle, which doesn't have a name, I think, but right, that's where he put this into a Monte Carlo simulation. So he doesn't describe how to do that, but basically he's going to take the probabilities wherever I wrote that from NMR, like what's the probability of, or how many of these things there are as a function of time. Right, so he has this reaction that happened, and he's going to say like he can get a probability of reaction, like probability of NH2 going to NHO, and then he can do the probability of NHO going to NOO, so that he forms a network. Right, so you can get all the probabilities of those things, and then he can say that he's going to go in, and the two things meet, and then there's a probability that that reaction happens, and he's going to roll a dice. Or let's see, there's a probability that that will happen. Let's work at a given temperature. What's the guess thing here? Something has to be 100% that it happens. I guess he's rolling the dice to see if it happens, if it matches that probability, and then it's like yes or no. If it's yes, he says it reacts. If it's no, he's going to take somehow KT and then some energy. He's also measured the energy of these reactions. So he knows the energy, so he can do exponential minus KT and get a probability from that. Well, that's what it is. He's got the energy of reaction, KT, and the energy of reaction. He gets a probability from that. Then he compares that probability with rolling the dice. If it's above the roll of the dice, he accepts that. If it's below, somehow he uses this temperature to decide. So that's a Monte Carlo thing. Actually, I don't have a good picture of how the Monte Carlo works here, but somebody's using a Monte Carlo method to grow these networks. Right? So you can grow the networks. He knows the functionality, F is 4. He can get kind of the molecular weight of these things as they grow, and then he can use the Flory-Huggins. There's a lot to this thing. It's pretty good in that sense. He uses Flory-Stockmeyer equation. So Stockmeyer is a guy from Dartmouth. He's dead now. And then Flory's a guy who won the Nobel Prize. And then they had, for this kind of reaction, they came up with these equations for the gel point. And these are the P's of the probability. A reacts, probably B reacts. So he gets that from NMR. F is a functionality, so it's like 4. They can get the percolation point of this thing. Gelation occurs if the A is how far the reaction's gone, like the percent of the units that have reacted. So at that percent of units that have reacted, if that's 1 over 4 minus 1, so 1/3, then the thing is percolated. That's the theory, the Flory-Stockmeyer. So he can say how much it's reacted from his Monte Carlo. He knows its functionality. He can predict where the gel point is from that, from using the NMR data. So he does that. That's what this triangle is. He predicts that. And it's pretty close. So you can convert the reaction, the cure time, because he has some other data. He's got viscosity versus complex viscosity versus molecular weight from his X-ray measurement. Then he also has the actual viscosity versus molecular weight from a rheometry measurement. So there's a lot in this. So the dots are his watching the beads move around viscosity, and the lines are his measurement on the viscometer, right? And they like match up perfectly, except down here. And he says down here, it's because the stuff in the actual viscometer, the low molecular weight components, the P tall thing evaporates. So this mono or difunctional, so two H's react, so it's difunctional amine evaporates. And when that evaporates, he gets a stiffer network or something, and that makes this thing shift. So he can explain why these disagree. There's a lot to this paper, right? The other thing, he's using something called a multi-frequency rheometry measurement, because on the time scale, the rheometry measurement, which is going to be like 20 minutes, the cure actually really does happen. So you can't do multiple frequency scans because over the time of changing the frequency, the stuff has cured. The X-ray is fast. It's a 20 millisecond exposure. X-ray is like, you can do 10,000. They do 10,000 2D exposures, which are 10 megabyte each in basically a minute. Yeah. So it's like they're generating like so much data from this machine. You have to kind of imagine that. So, and then they have to do correlation functions on it. But so so instead of wiggling the thing at a frequency that's going to look like that, they take, so they want to do all the frequencies at one measurement. So they superimpose, this is something like the modulated DSC, where you have a temperature ramp and then you superimpose on it a sine wave. It's the same idea. So you can just couple up different signals. So here the signals are frequency. So he's got like a bunch of different frequencies. He just adds them all up, right? And then you get something that looks like that. And from that, I guess they do like a Fourier transform and decompose it, get back individual frequency responses from the thing. So you can do all the frequencies at one. It's not going, it's going like, you know, it's got all the frequencies together. Then the signal you get out of it, you mathematically get back your thing. So that is described. So there's a lot of stuff to this. That is described in something here. Not this. This is for the dynamic light scattering thing. Multi-wave rheology. So what is it? TA Texas thermal analysis, I guess, not Texas. So they just say how this works. Like here's their adding together what I was trying to draw, and then that's the sun. So it doesn't look anything like it. But from this, applying this kind of noise to it, and if you analyze it and Fourier transform that, you can get out the signal from all your frequencies at once, apparently. Like it seems like that's questionable if that would work. But you can see so he did 5 frequencies at the same time. So he's oscillating it with 5 frequencies. So it means he can instantaneously get 5 frequencies as the thing's curing. So he's got 5 things. So he has 0%. So this is a tight network, 0% of the difunctional that makes linear polymer. And this is 100%. That means he only makes linear polymer. So when he has linear polymer, he gets a difference in frequency of the viscosity. That means it's like shear thinning. So the higher frequency has a lower viscosity. It's like the green one would be the lowest frequency, I guess. But actually the black should be the highest frequency. So I should have, the low end. The highest frequency should have the lowest viscosity. So I'm not sure why the black one's the highest here, but anyway, the black is definitely the highest frequency of the particle motion. You can see there's a gap between them also. I mean, the gap is mostly the evaporation, he says. So anyway, there's a lot to this paper, but you don't need to know all of it, but just kind of glancing at it is good. What else is in here? This plot is kind of interesting. So each of these color things is a time sequence for the gamma, right? So he's got this kind of time sequence of the gamma. He's showing when the gamma goes through this transition, or when I guess it's a time sequence of the tau, it's the relaxation time. So when it stops relaxing, he's reached his cure point. And that coincides with this time gamma -1 curve, which is this black line here. So like where this, in other words, the exponential fit of this curve gives him this gamma. That gives him the cure point of the material, where it goes from where you go through this relaxation. Then he matches that with this cure point in terms of what tau. I think these are the rheometry curves, like to see. So the two things match up. It's kind of an odd plot, but it's got information in it. And these are his two showing the power 2. So he says 2.3, but this is gamma versus q squared. So if it's a straight line, it's power 2, but it's a little bit different, so it's 2.3. This is like a power 1 on a plot that's intended to show power 2. So you can see like a log plot probably would have been more effective here, because it's not like you could say that's 2 with some kind of deviation, and that's 2 with some kind of deviation. But anyway, I think a log would have been more convincing there. I think he shows log in the supplemental for this thing. That's log linear. That's his G2 curves. Yeah, he never shows log, he just shows it versus q squared. So, forget what else is in this thing. It's pretty clean work. I mean, I think it's pretty good. But there's nothing like profound in it, but it's just like good, clean work. Let me just see what the questions are. Let's see what mess is giving you here. It's pretty involved, so it might take some time to go through this. So this is just asking what is a 2-time correlation function? Like, what is he talking about there? He uses a 1-time. He uses it, and he explains why he uses it. He says it doesn't change. Like it's in the time scale that he's measuring the XPCS. This correlation function isn't changing anything, so you can just use it 1 time because it's like so much easier. And the other one probably would be hard to understand. Similar to DLS, except he's got this power, the compression exponent, fragility, and why is it 2 and 1? So 2 is the diffusion and 1 is ballistic, and it's whatever explanation. 2 is a normal and 1 is abnormal. And it's 2.2 and it's 0.97. You could talk about this if you want, or you can just say like diffusion. And then so just what is this multi-wavelength rheometer and why would you use it? Basically, if you want to get a frequency dependence and something that's changing, that's the way to do it, so any kind of curing system. And then changing the exponent P with crossover. Oh, okay. Then the oscillatory rheometry shows the, let's see, that's in the supporting information. So that's important. So, right, so this is a normal rheology thing. So you're plotting G prime, G double prime. So G prime's going with power 2 of frequency, G double prime power 1, and that means flow. Like in that region, you have flow, right? And then When G prime becomes larger than G double prime, that's where it gels. That's where it kind of forms a network. So then at that point, G prime solid, G double primes kind of flow for the viscoelastic. So it becomes a solid here, right? And that's the crossover points of frequency of the time when it gels. That's a percolation time. Right. So, and there's another crossover out here that has to do with reptation within the network. But so let's see, where's the question here? Changes in exponent P, the crossover time for cellular rheology, and the prediction for the gel point from the Monte Carlo simulation. So that's a triangle thing. There's no change in the gel point. So if you look at this, where that plot is, it's the last plot actually. So, so it's got like the three techniques in it. So you have that transition in the P, it goes from 2 to 1. So it goes from diffusive to ballistic. Then these numbers are at the 5 frequencies that he ran, right? So different times for where that crossover point is, like where it gels. And you can see it's exactly the same place. It's like beautiful. I mean, there's no reason why that would work, right? I mean, it's a messy system, right? So one thing is that this is supposedly this system that's got these like clusters of things. It's a complete mess. Like people would think of this as just garbage, right? Nonetheless, so he's going in at a 50 micron, like the size of a hair spot, right? A diameter of a hair. And he's measuring. And then the other techniques are using the triangle is atomic scale, so 50,000 times smaller, right? And it gets exactly the same transition point. And then his dynamic rheology is somewhere in between those two, and it gets exactly the same transition point. That means it's completely uniform. That the only way that could possibly happen is if there's absolute complete uniformity in this system, right? Up from 50 micron down to an atomic level, which is basically the whole game. So, so anyway, that's really surprising. That from this, and he doesn't emphasize that, but basically that's really surprising. Like, because people think of this as just goo. Like you just put the goo on, you make the sailboat, it sails. That's good, right? They don't think of this as like a uniform system we could study this way. So then, anyway, so it falls apart when he goes. This becomes a broader range, and the frequency dependence shows up when he gets to linear polymers, right? So that means that the viscosity has a frequency dependence. So we know what that is. Like you're looking at this kind of curve, like you plot the log of the viscosity, log of the frequencies, you have the plateau, the Newtonian plateau, and then it's going to have this power law fluid. So the viscosity goes with the shear rate or the frequency to some power. Right? So that's power law fluid behavior. So that's like the normal behavior for a linear polymer. So he sees that's his frequency dependence. And if you did a log plot of this, the slope of that would be the power law fluid decay. Right. And when it's a network, he's in the plateau where it doesn't depend on frequency. So that means it's solid. It doesn't have any decay. So this happens because the chains are straightening out. And here the chains aren't straightening out, right? So it's just a single value. It's neat that he can see that, right? It's a pretty complicated measurement, and it just comes out that that's how it works. So, and it also, his XPCS measurement also broadens out, so he's seeing also that maybe the different size beads have different response or something, and they get this broadening out of that. And his simulation, even the simulation, the NMR kind of matches up. So the whole thing is pretty neat I think it's neat that what he did. It's not like earth-shakingly profound, but it's really clean work. And it's kind of worth just looking at kind of what he did. That's that Flory Stockmeyer wiki page. And then let's see. So figure 4 compares oscillatory complex rheology at 5 frequencies. But divergent longer cure times or reasons for, so that's the reasons for that. Figure 4. What is figure 4? That's figure 8. figure 4. So so the divergence is because of this, as you go up in the linear one, it becomes more linear and it's got this spectral dependence, but also there's this transition here because of the evaporation. He mentions it in the paper. That's all. That one isn't really a big deal. So anyway, there's a lot you can get out of this paper, but just kind of glancing at it, it's probably worthwhile. And it's got this kind of dynamic light scattering kind of function in it. So it's got a lot. The other problem with it though is that so there's a guy named Weiss, right, that invented diffusive wave spectroscopy with light and using the particle thing. That was the first particle tracing experiment. He was at Penn, University of Pennsylvania, I think in like the chemistry department. And then this guy Mason, who's at UCLA, I guess. I'm not sure what his relationship was, but he published with this guy Weiss. And then this guy Tom Squires, who's at Santa Barbara. Anyway, somehow they've written the paper that they reference in here to talk about this kind of dynamic light scattering. You can see the White's thing here. So it's like Mason and White's 95. That's like the original papers of this. And Pine is at Harvard. It's like Weiss is Penn, Pine is Harvard. So this is like big schools, I guess. And at the time, people thought it was like nothing important, I think, for the most part, until they realized that the measurement could line up exactly with this mechanical rheology, like they fall on top of each other and they can access these really high frequency things where the mechanical doesn't work anymore. So then all of a sudden that became important. Then they realized like you can do this with X-rays and neutrons. So then it becomes even more and more important. And it's a pretty powerful technique given that it's seems like a stupid idea, you know. But anyway, I mean, you got to throw particles in. It's definitely going to perturb the environment. So there's problems with the particles disturbing the system. There's a lot of things with it that make it seem stupid, but actually it works great. So anyway, the Weiss, if you read the original Weiss stuff, he relies and he spends a lot of time talking about multiple scattering. So his whole theory depends on this idea. So you have a beam of light that comes in, it hits a particle, that goes over and hits another particle, that hits another particle. So Weiss's theory, the original theory, relies on multiple scattering. So the other option is you have one particle and it scatters, right? And then you can get the pattern from it that comes out. Right? So these are interferences between waves, right? So basically it's not just like one, but so anyway, there's a difference between multiple scattering and single, and usually single is the thing you want, right? So to get multiple scattering, then you have to put in a lot of particles. The more you put in, the more multiple scattering you get. You can see this effect. Like you have a laser, and then you have a clear piece of paper or something, or clear plastic, and then put it on a screen, you'll see the spot of a laser. That's not multiple scattering. And then if you put a piece of paper in, then that becomes like nothing. Like you kind of see it's brighter in the middle, but there's no beam anymore. You can't identify where the beam was, right? That's multiple scattering. That means that the information, you can't get information out of it. But it means that Weiss assumed that you get this diffusive pathway through this of the beam, and then somehow that gives them this ability to measure the rheology from it. That was Weiss's original thing. This paper, they use 1% of these polystyrene beads. This is monodispersed beads. It's something like 25%. He mentions that like everyone else has used 25%. We're using 1% because they think that 25% perturbs the epoxy reaction. It's probably true. No, 1% doesn't. And he demonstrates it doesn't because he runs it. It does the cure and the rheometer with and without. That's what I mean by he's covered every possible question to this, except there's a few questions like why do you use polydisperse? 1% is the Weiss's main assumption was that it had to get multiple scattering. 1% won't do that for you. So especially with X-rays, because the contrast with X-rays is much less than with light. So this multiple scattering effect, the bigger the contrast you have, the bigger multiple scattering effect you have too, for some reason, because they scatter more, and then they can multiple scatter more. But if you have something that's got a very low contrast, like X-rays, so X-rays have a really low contrast compared to light, you know, so if you convert like electron density to index of refraction in terms of the intensity that comes out, it's much lower. So anyway, you have a couple problems with doing this dynamic measurement with X-rays. The contrast is too low, and then he even drops the concentration below the 25% that would normally be used for this diffusive wave spectroscopy. So I kind of question like what happened with that too. Polydispersity and that, but I'm sure they have answers to that because they're pretty bright. Like the guys that did this were really bright. They did a really clean job. That's something that seems like there's nothing more to get from epoxy. It's just goo that you put in, but actually it isn't. You know, they showed that it isn't. They showed that it's actually uniform. You know, so I think it's a pretty good paper. I mean, it's not like some flashy thing, but it's important to people making airplanes, I guess, and surfboards. And anyway, you can kind of look at it if you want. There's a lot of papers, so I think you can answer the questions without going too much into depth for it, you know, if you want, or you could look at all the stuff in it. There's a lot there, so either way, it's okay. But, so that's about it. Any questions, anything? But hopefully it's close enough to what we're doing that makes sense. But all right, have a good weekend. I guess Mike's spending a lot of time on these things. I think that